So we're going to talk about a new thing, or a thing we haven't had in a while, some new science in Friedreich ataxia. We have two stupendous speakers here today. The first one coming all the way from lovely Oklahoma City or Norman or wherever you officially call the University of Oklahoma. It's my privilege to introduce Dr. Sanjay Bidichandani. And you know, I just love saying that name, so we're going to say it again, Bidichandani. You didn't realize it could also be a verb, but that's a different story. So Sanjay's you're still head of genetics at the University of Oklahoma Medical School. He's been a friend of mine for too numerous to count years. The most common of the questions I received today, the most common answer I have had the privilege of giving is, watch the talk this afternoon and Sanjay will tell you your results. So with that in mind, tell them the results.
Thanks, Dave. I was concerned when he said stupendous. That was a good end there. Okay, so I've titled this talk, Typos in the GAA Repeat, and why the typos might matter. And so, you know, a lot of people sitting in this room have had a genetic test for FA. And I don't think many of you have actually seen what a test looks like, or you don't think about it anyway on a daily basis. So because these typos that I will talk about have very important implications for the diagnosis of FA, I just want to start with just showing you what the gene looks like, this GAA repeat that everybody talks about, and what the test is that we do to actually assay this test before we get into what these typos are. So we'll first look at the DNA test, then I'll tell you about the typos, and then we'll start discussing as to why this even matters to us. Now, this is the gene, the frataxin gene. It's actually quite a small gene when you think about it in terms of the other genes in the human genome. And in the first half of that gene, that triangle that I'm showing you there, is the GAA repeat sequence. And as long as this repeat is less than 30 triplets, it doesn't cause FA. Now, we've heard this before. What does it look like? So you can actually read the sequence. You can sequence it, and if you look at it, you can count. It's 8 times GAA. So you get 2 pieces of information here. You know it's 8 triplets long, and there are no typos in here. It's a very clean GAA, GAA, GAA. And you can have longer sequences, and as long as it's less than 30, nothing happens, okay? Now, of course, FA is caused by an expansion of this repeat, right? So you go from 100 to 1,500 of these sequences, and you have to get one from mom and one from dad. Now, these sequences are a bit too long to actually read through. And because people don't have the ability to read through this GAA sequence, we've so far used indirect ways to measure these repeats, okay? So you actually come up with some estimate for what the length of this is, and based on that estimate, we tell people, you have 500 repeats and 800 repeats and so on. Now, the strategy actually is not exactly like that, but for all practical purposes, what we're doing is we are cutting out this sequence, and we're going to run it through a gel. A gel is literally like Jell-O, okay? And what you're seeing here is a gel, and it has 5 lanes, and each lane, we're going to load what we've cut out of people's DNA and put it into these lanes. And so if you look at the very last lane, the last 2 lanes, 1 and 2, that's 2 different people who have FA. And in each of those lanes, you can see 2 bands in there. There's 2 bands there and 2 bands in the last one, 2 bands there and 2 bands in the last one. So what does that mean? Well, this gel is actually providing some kind of resistance to this band. So the smaller bands run faster and the bigger bands run a little slower. And in the first lane, we have some size standards. And based on where these bands end up, we say that this person has 480 and 850 repeats. And so everybody sitting here who has a DNA test for FA and they've told you you have 800 repeats and 1,000 repeats, this is how they're telling you that you have 800 repeats and 1,000 repeats. Now notice here, as opposed to that sequence that I showed you, you can only tell the size of the repeat. You cannot actually tell the exact sequence of the repeat, right? We just have to assume that based on this size, there's 500 GAAs in there or 800 GAAs in there, but we don't know that they're actually GAA, GAA, GAA all the way because we haven't actually read through it. We cannot read through it, or we haven't been able to read through it. Okay, so this is how genetic testing is going on today. Now, typos in the GAA repeat. Now, there's actually new technology that actually allows us to read through these long sequences now. So on the left, you can see the most common way in which genome sequencing works is you read in short read sequences. So if you have 30 repeats, 20 repeats, 18 repeats, you can read right through it with this short read technology. But now we have this new thing called long read DNA sequencing. And so we figured, why don't we use that for FA and actually look at the repeat and see how long it is, but also, is it actually GAA all the way? Okay? So here is an example of long read sequencing. Now, instead of showing you two bands, we can actually see two boxes here. The boxes are all shaded in blue because GAA has been given a blue color. And so what you're seeing here is 800 and something and 400 and something. So that's two expansions. And it's all blue, so it's pure GAA, right? So this new technology is actually pretty cool. We can actually not only say that there are these two expansions, but we can actually look at the GAs and know that these are GAAs. But then we found this kind of sequence. Now what you see here is one of the expansions. This is the second expansion. So this person has FA, has two expanded alleles, but the top one here has this huge green box in the middle. That's not GAA. It's actually GGA. Now I know most people go like, it's still G's and A's, right? Why is this guy getting so excited? What's the green color about, right? Actually, it turns out that G's actually make DNA stick together really hard. So instead of GAA, where you have one G per triplet, now we have two G's per triplet. So people like me go like, no, that is a big deal, okay? You'll see in a second why it is, okay? The point is, we now have seen this sequence. Now I'm calling these typos for this meeting, but actually we've given it a technical name. We're calling it a chimeric GAA-GGA sequence. And we've actually found many people who have this now. 15 to 20% of people with FA have at least one of these sequences that have a typo in them, okay? Okay, now, the main question is, why should we care about this, right? Why does it matter? And to get to why it matters, I just want to show you how we discovered this first, and you'll see why it matters better when you start to see how we found these guys. So if you remember, this was the genetic test. This is the genetic test. This is how most people are diagnosed with having FA, is by doing this kind of PCR analysis, and it's basically cutting up the sequence, running it out on a gel, sizing it, and telling you you have FA because you have two expansions above a certain threshold. I'm going to add two extra lanes past that. Right? Now look at lanes 3 and 4. Now in these lanes, you see only one band. And a diagnostic lab looks at this and says, because you have to have two genes. And so they say you must have 900 and 900, or 1100 and 1100, because they're both running right on top of each other, and they're not resolving into two separate bands. And so some of you who know your repeat lengths might actually know, I have 800, 800, or I have 1,000, 1,000, as opposed to two different lengths. And so we were kind of intrigued by this, and so we wanted to know how many people have this type of pattern. And so working with Dave, we screened 112 unrelated people with FA and found a quarter of the people have this type of pattern. Look at that, so many people with just one band, and that didn't sit right with us, okay? So we're like, wait a minute, maybe we are missing the second gene, at least in some of these people. a valid question. So we said we want to do long-read whole genome sequencing. We just want to find what is going on with both the genes, okay? And the only problem is to do each of these long-read genome sequences, it costs $1,200. So we called FARA. And you heard today from Bridget. Bridget said FARA gave us $75,000. So we were able to sequence a lot of people to see if, what is going on? What do they have? And the first chimeric repeat that we found was in one of these people. And what you're seeing here is this bottom portion that's pure blue. That is the only product that you can see as the visible product. Remember I told you a quarter of the people you see only one band? That one band that you're seeing is this pure guy here. You're not seeing the chimeric allele. So a lot of the people who have 800, 800 actually have one band that is 800 that is pure, the one that you can see, and they have this other chimeric allele that diagnostic labs are not seeing today. No, there you'll see a single, I'll get to that later, yeah. So the point here is all these other chimerics that I showed you, they're all seen in people who have these single bands. If it's not clear yet, look at this gel. So this is a person who has a single band, and now we've come up with a new way to actually analyze this DNA. And this person with a single band now shows up as being a double band. So here's the really important part. A lot of the people who have 800, 800 or 1,000, 1,000 as their result actually are 800 and something else. And that something else has to still be determined. And this is about 15 to 20% of people with FA. So this is why we care about these typos. It's interfering with the standard genetic test, and we have to be able to do better in terms of assaying what the actual repeats are in these people. Okay? So that's the first thing. So we've actually shared this information with a lot of technical, like with a lot of labs. We've also it's out for review right now. It will be published soon, hopefully. And then a lot of the diagnostic tests will actually start using this. So going forward, we will have a better genotype, okay? We've also come up with a new long-read sequencing strategy that costs less than $100 instead of $1,200. Thank you to FARA. And so this might be something that others might use to actually characterize the spelling mistakes better. So not only will we know what their real repeats are based on a test like this, but we'll also be able to categorize what kind of chimeric allele sequences there are, so we can actually start to ask a bigger question as to how that affects, does someone with a chimeric sequence progress slower? Do they have later onset? Do they have questions of that nature, okay? Now, remember that a person who had the single band, while we didn't get the repeat lengths correct, or some of them are still not getting the repeat lengths correct, but the diagnosis is still correct. They do have FA, right? So there's nothing wrong in terms of, you still are going to get the diagnosis of FA, you're just not getting the repeat lengths correctly. But the same concept of missing a chimeric allele has a very different impact when you're talking about carriers. Because in a carrier, if you are missing a band, so for example, look at this family here. This is a child who has a single band. Mom is a carrier because she has this expanded band here and a normal band down here. Dad actually doesn't look like a carrier at all. But when you do our new test, now Dad looks like a carrier. So this means that relatives of people who have these chimeric alleles, some of them are being told that they are not carriers when they actually are carriers. So that's another reason why we care about these chimeric alleles, is that a better test is needed for carrier detection, so we are not missing some of the carriers. And Eric, to answer your question, this is what someone with a point mutation would look like, a normal and an expanded. So they would not fall into our category of, okay. Now, the bigger question is, what about all the people who have these chimeric alleles? Do they have the same age of onset? Do they progress slower? Now, while it's still early to answer that question definitively, and here's another use of the natural history database, a natural history study. And here is, now this is a complicated graph. Okay, so what you're looking at here are in the large, so this is called the FACOM study. This is before the current Unify study. So this is natural history purely at CHOP. And in this whole database, at the time that we assayed, that we designed this graph, we had, I think it's 304 loss of ambulation events. So each dot there is a person with FA who has lost the ability to walk. And on the y-axis is the age at which they lost the ability to walk, and on the x-axis at the bottom is their repeat length. Now, you notice there are two types of dots. There's red dots and there's blue dots. The red dots are people who have two bands. They have repeat lengths that are of different sizes. So they've been told you have 400 and 800, or 800 and 1,000. And the blue dots are the people who've been told they have only 800, 800, or 1,000, 1,000. They have two of the same size. Now remember, the second group, about 40% of them actually have chimeric alleles. And if you just separate these two types of people with FA, you notice that the people who have that single band pattern, they have a 3.9 year later loss of ambulation, suggesting it might be a slower progression. Just wanted to take this data with a pinch of salt at this point. Not everybody with the blue dot has a chimeric allele, but the blue dot guys are the ones that will have the chimeric alleles. The red dot guys will not have the chimeric alleles, okay? And so this is telling us we need to look a little bit carefully at how these chimeric alleles affect the phenotype, I mean the presentation of people with FA. So this is the reason why we care about these chimeric alleles. So just to summarize, 15 to 20% of people with FA have this new type of GA repeat that have these typos in them that we are calling chimeric alleles. And we need a better test to actually identify these. We have the test, it just needs to be implemented and used for people. And there's the possibility, unfortunately, of some false negative carrier testing where some people have been told they're not carriers when in fact they are carriers. And then the last thing is chimeric alleles may affect the phenotype, perhaps making the disease progression a little bit slower. And thank you very much. I'm happy to take questions. Before I say anything else, I want to thank FARA. As you see here, that $75,000 grant that we got from FARA, as Bridget said earlier, got converted into a $2.8 million grant from the Department of Defense, which Dave and I got to take this thing further, to make this analysis that we're talking about possible. So we'll make this be the way people get tested. We'll try to figure out the phenotype and see if it makes a difference. The work that was done here was led by Morgan DeVore, who's my PhD student, and there's Christina, who's the lab manager and a chief technician who actually did a lot of the cool PCRs that you saw. This work would not have been possible without Dave and his group here, Courtney and everybody else listed there. And you can see these two boys there. We're at a ride event here, and I don't know if you can see, but those two caps that they're wearing actually have ride Ataxia symbols. This was actually made by Lane Brodden, who used to work at FARA before. And both of these kids, they don't look very excited to be there, but but hopefully as they grow up, they'll realize the value of that cap they're wearing. So thank you very much.
Take a few questions. Does anybody have any questions?
At the back there.
Thank you. I understood about 4% of that. So with what I understood, as you're talking about negative carrier results where you could be a carrier and how we might be looking at the expansion differently, what does that mean for us in the day-to-day, right? Should some of us look at retesting? So that's the first thing that comes to mind, and maybe I went too far, but that's the first thing that came to my mind. And then the second, which you probably can't answer, but I start to think too about like design therapeutics, if we're looking at addressing that GAA repeat, and now there might be new things with that repeat. So my mind is going lots of places, but the first thing I thought was, what does this mean for us, and what do we need to be mindful of as a community so that we are well educated moving forward for our kids' care and our own life choices?
Yeah. The second question was actually an easier one, which is to do with the design therapeutics drug. And the question is, the design therapeutics drug is designed to come to the GAA repeat and bring with it the ability to restart the gene, right? And so if it's being attracted by the GAA, but here you have a GGA, how is that going to work? Now remember that almost everybody who has this chimeric allele, the other allele is actually a pure GAA repeat. So when the design drug comes, even if it's not going to work perfectly on the GGA sequence, it still has the other gene to reactivate. And so this one is not going to be zero, it's going to be a little less efficient. So overall, I think it'll still be fine. So that's for the design question. I think, see, there's two ways to think about this. One is going forward in terms of testing, right? So once our paper comes out, all diagnostic labs get to see it, and they're pretty quick about changing their protocols. So going forward, I think testing will become more accurate, and this will not become an issue anymore. Now, the question is about legacy testing, people who've been tested over the past 20 years. Like, what do we do there? And I think that's a more complicated question to answer when you think about everybody. But at least with CHOP, for example, we are going through the whole database there and actually working with the people who we've identified as having chimeric alleles and testing some of the people in those families to see what's going on. So that is what this DoD grant is supposed to be for, is cleaning. That doesn't solve the problem for everybody else in the world who's not at CHOP, right? And so this is a bigger question to answer in the community. And I think that's a conversation one needs to have. It's not a straightforward answer.
So you answered the question for the one study that's underway, but if you're one of the people who might have the weird zone of 2, not 1, is that something you should get settled before deciding on doing a testing? Are people that are choosing candidates for testing aware of this and know to look if they only have the one showing up?
So the good news is in about 150 people we've tested, we only have 2 people who fit in that category where they have both alleles that have the chimeric allele. So this is an exceedingly rare situation to have both of them have the chimeric allele, okay? Now, we don't have direct evidence to show that the design drug doesn't work as well with this, so I don't think we should be raising alarm for no reason at this point. That's something we'll have to do experimentally to verify to see if it actually is less effective. So I just leave it at that at this point.
So is Dave in the room? Is he?
Dave is here.
So on the natural history, I noticed it's Norm over here in the corner. I keep moving to
The
confuse
natural
you.
history person, yeah.
So in natural history studies, I mean, in FA Woodstock, we took bloods, we gave to FARA. You did the analysis even for us parents, siblings, everybody. Is that something that you're going to continue with the new expanded test now for natural history? I'm trying to get people to come more for you.
We'd love to continue it. The grant from the Department of DoD, or if you want to use the more modern terminology. No, okay. Then
That was an immunization.
yes, immunization, exactly. We will do it, except that those are, for example, we actually drew one sample today that Sanjay had requested on a parent of one of the individuals on that graph. It has to be drawn and sent fresh to Oklahoma to arrive by tomorrow. No, it's not getting on his plane. It's in a FedEx box on the way to the lab tomorrow. So it takes a lot more technical effort, even for that relatively cheap $100 test, that FARA should be so appreciative that Sanjay's developed. So it's not as easy as doing it for taxon level. But one of the aims of the DoD grant is to go back and look at frataxin levels in peripheral tissue, blood basically, and see if they can be predicted better using the new repeat links which we would create. But then you get the question, how do you count that new repeat? Do you count it from the longest uninterrupted stretch? And that's why we have to accumulate a lot of samples, which you are trying to get for us right now, where he can draw more blood and send more blood to Sanjay, and he can do that so wonderful $100 cheap, inexpensive test. So we will need more samples. We always need more samples. But you can I'm not going to bring up anything about design other than to say we brought up that question and we have gone back to look at the sample. Many of you gave samples to us, which we sent to design to develop their drug originally. We have gone back to look and see. It turns out we didn't send any two identical repeat people to design for development of their drug, so I can't tell you anything from the samples we sent.
Gotcha. Because I was thinking about for the pharmaceutical industry, if they're going to have to re-look at their data set, and these might be outliers.
It is conceivable that outliers in the past might be explained by this. It's conceivable it might not be. Jamie has someone. Chandra.
I think my question was a little bit answered, but I was wondering if the trend of slower progression that you're seeing is only in people who have like a chimeric GA1, or if it's like a chimera in either allele. If that makes sense.
Yeah, so your question is the dot representing the shorter repeat?
No, so like on your graph, you have like the people in blue dots who have like a chimera that seem to have potentially slower progression. Are those dots representative of people who have a chimera in GA1? Or are those dots people who have a chimera in either allele?
Yeah. So again, huge note of caution. We do not know the genotypes of these people in terms of whether they have chimeric alleles or not, okay? So now we're just projecting and say, let's think about who might have chimeric alleles. We know 40% of people who end up with a single band pattern, we know that they will turn out to have a chimeric repeat, okay? Now, those blue dot people are everybody who has a single band. They've been told they have 800, 800, or 900, 900. So not all of these guys will have chimeric alleles, but chimeric alleles will be concentrated or will be overrepresented in the blue dot group. But the red dot groups, these guys have two bands. They're very unlikely to have a chimeric allele of any length that is worth talking about in this context. So a red dot is going to be somebody no chimeric alleles. Blue dots, many of them will have chimeric alleles. So we don't know whether they definitely have or not. Now when you separate it this way, you end up seeing this difference in phenotype. Now remember, this is actually pretty impressive because the people with short GA1 repeat alleles, they're going to be mostly in the red dot guys. So that's actually going even further because those guys should be milder, right? So even then we are seeing this 3.9-year difference. Again, note of caution, we don't know who actually has a chimeric allele.
Got one question for Sanjay and Dave. That is, if it turns out, as you suspect it appears, that the chimeric allele leads to slower progression, is it possible that that introduces a new therapeutic target, that we could introduce such interruption?
So the bigger question, remember, these people were all identified as people with FA. Nobody had suspected, at least, that these people were going to be greatly different. In other words, people with 900, 900 were not considered that different from somebody with 900 and 1,000, right? And so if you're going to think about it as a therapy, it's going to be a very mild therapy, right? The actual way to think about it is if somebody's trying to develop a therapy by saying, I'm going to make interruptions happen, I'll say there's not that much payoff here, is how I would say it, yeah.
I understand how the data would hide in the two ones that had equal repeats. But why is it not possible that people who might have 900 and 1,100, why is it not possible that one of them could also be a chimera, but just not seen?
Yeah. So the question here is, how can we be so certain that the red dot people who have 900 and 1100, that they do not have chimeric alleles, right? And so I didn't share that here, just, there's only so much one can talk about. We've actually done a whole cohort. Once we got that $100 sequencing assay, we've done something like 80 people who have 2 different bands, and we found maybe 2 or 3 people in there who have very minor changes in sequences that we would not define as our chimeric alleles. So I would actually say that is the reason to say why the red dot guys are very unlikely to have chimeric alleles. Yes.
Thank you, Sanjay. Very good.